Hi everyone. In today's video, we are going to discuss two important RNN architectures, one of them being LSTM, and this LSTM creates a basis for a lot of other architectures which people are using these days, and the other one being GRU. So we will first start with LSTM and try to understand how is it an enhancement over the existing RNN architecture we were having. So the existing RNN architecture from the part 1 of this video series used to look like this. We had an input variable xt over here. We had the value of hidden state at the previous time step, and there was definitely an activation function f which we are writing over here. And based on the value of the current hidden state, we were able to estimate the value of yt. So there were some parameters u, v, w, b, and c. And the only constraint I could see over here is the fact that the hidden state at time t is dependent only on the hidden state at time t minus 1. We can write a lot of other functions, or we can increase the number of parameters to make sure that the hidden state at time t is dependent on some n number of time steps, like it may be like st minus 1, st minus 2, and so on. But on doing so, there is going to be a drawback. First, we may have a lot of parameters to tune, and we may end up in a scenario where we have exploding or vanishing gradients, a concept which we will discuss in detail when we talk about backpropagation through time. But as of now, in part 1 as well as in this video, we are just going to understand how the forward propagation in both RNN and LSTM is going to look like. We proceed further to the LSTM domain, and we start describing few gates which are associated with LSTM. The first gate which we encounter is called as a forget gate. It's better as of now not to see the entire architecture in the form of a diagram to make things much simpler. But if we are observing things in terms of numericals and equations, it will be easy for us to correlate in later steps. So the forget gate is ideally outputting something like ft, which is a value which lies between 0 and 1. And this is a probability that how much of the previous hidden states to forget. Just to give a very relevant example, let's say you start a year and you start studying a particular subject from the beginning of the year, and you are at December 31st. Obviously, you won't be remembering what all things you have studied in each and every day of the year. So, definitely, there are few topics which you might be forgetting, a small proportion of it, depending on how much a human brain can retain. The similar functionality is attained with this forget gate, where it says that we have learned some amount of information till a particular point of time. I can retain only a certain amount of it, and then I will better forget the non-relevant information from the memory. So the value of forget gate close to 1 will mean that the entirety of history could be removed, and the value of forget gate close to 0 will mean that a significant amount of history needs to be remembered. For instance, if the value of forget gate is, let's say, 30, so it will mean that around 30% of the information could be forgotten and 70% could be retained. So on doing so, we follow the usual way of writing the association between the networks, that at any point of time we have a state ht minus 1, which is which was written previously as st, but over here we use ht minus 1. St is used for something else. We have xt, which is the input at time t. Like we used to multiply the xt with u, we will multiply with uf. This is a parameter which is going to be tuned, and like we multiply st in the part 1 of the video with a matrix w, we multiply with wf, and there is a bias term bf over here. And now, since it is definitely going to be a value between 0 and 1, the only activation function which can help us achieve that is a sigmoid activation function. So we use a sigmoid activation function in the forget gate. And the explanation is written over here. I will share the notes in the GitHub link of the video. Like, the forget gate will decide how much of previous hidden states to forget and how much of new information to retain. And this is the new information which we are talking about. And the previous hidden state is mentioned over here. Like if I am on day 200 in a year of 365 days, it will tell us how much of the previous 199 days we can forget and how much of the current value we need to retain, that is made sure by this term UFXT. Now we come across another gate which is called as an output gate. So before going to the output gate, we just spoke about a gate which is called as a forget gate. So the amount of information which it needs to forget, and the amount of extra information which it needs to remember is put in something called as a cell state. The cell state holds the amount of information to be kept in the network, and the output state will regulate the flow of information in and out of the cell. So just assume that you create notes while attending the classes and the entirety of the 365 days, and then you observe that okay, in the entire set of notes I will only create some subset of the notes covering the important topics, and as and when a new lecture is delivered I will just keep on updating the means top 100 or top 20 topics I should be remembering. So that thing is called as a cell state, and the inflow and outflow of, or basically the outflow of the information is taken care of by the output state or the output gate. So the output gate determines which information from cell state should be output to the current timestamp. Now, once we have an output gate, a forget gate, there is a new candidate for the cell state as well. And again, output gate is going to be a value between 0 and 1, and hence a sigmoid activation function is used. It's also a percentage telling how much of the information will be flowing from one state to the other. Now we have a possible combination of the cell state, and it is going to take the exact same framework as we had been doing. We take a hidden node, we multiply it with a matrix W, we take the input value, we multiply it with U and add B to it, and then we follow a activation function. By that we mean the potential input value which could be added to the cell state is called the new candidate value for the cell state. Cell state is definitely going to have a value, but a new candidate value could be added after some calculations. So this could be the new candidate value for the cell state which could be added, but we are not adding it right now. So again, this is a tan hyperbolic activation function. So not necessarily tan hyperbolic could be used. It could be also a sigmoid activation function as well. And then we proceed for further to say how exactly we are going to put forward the memory network at time t. Now there is so we talked about the forget gate which we are presenting over here. We talked about output gate which we are writing over here. There is definitely an input gate as well, which is going to take the same form as we have taken previously. So IT is going to be pretty trivial. It is going to be W I, and this is over ht minus 1 plus ui, I write it as xt plus bi. It is just the same format, and then I write a sigmoid activation function on top of it, and it tells us how much of the what is the percentage of the input information we need to add to the cell state. So this is how it goes. We just were able to find out that GT is the new candidate cell state, and this tells us how much of the information of the new candidate cell state to be added. And when we are adding it, definitely we are going to remove something from the cell state as well. So this is the previous cell state which we had, and this is the percentage of information that needs to be removed to accommodate this information in the cell. So this is how the memory network at time t works. So let's say that we have st minus 1, and we are forgetting like 20% of the previous information, and the IT says that we have to retain like 0.6 of the new information in the new cell state. It doesn't matter that IT and FT should be adding up to 1. It's not really needed. The only thing one needs to be a bit careful about is the fact that there is going to be a new candidate for the cell state, and we can't add it completely into the cell state. Only a little bit of it could be added, because definitely there is a forget gate which will modulate how much of the previous cell state values needs to be forgotten to accommodate it. Now if the forget gate is 0, this will mean that we will keep on adding new cell state information, and the ST will not be that you can say stable, and it will mean that we are just adding up or cumulatively adding the information across different time periods. So we proceed further and see that we have two states, cell state and hidden state involved. The cell state at time t is what we called as an ST, and the hidden state is we call at HT. So this is the layman definition of hidden state, which means that based on the input sequence, we process the sequence which is given to us, and the sequence could be anything. Either it could be like an embedding of a particular word, or the prices of stock market in different days. It could be anything, but we need to compress the information from the input sequence that could be passed to different states. Like it could be used in calculation of the hidden state, it could be used in the calculation of the forget gate, it could be used in the calculation of the output and input gate, and so on. So just hidden state plays a role in passing the information from the input state to the input, output, and hidden gates, while the state remains the amount of information that needs to be maintained for making a prediction. So that is the only difference between the hidden state and the cell state. So this is the input gate which I have explained over the period of time. And as I told you how much of the new input it needs to be incorporated, it is like present over here. And now we talked about the updation of the cell state. This is how the updation of the cell state is going to look like. But we didn't talk about how the updation of hidden state will look like. But we did use the hidden state from the previous time step for the calculation of forget gate, which eventually was used in the calculation of the current cell state. The hidden state from previous time step was used in the calculation of update gate as well, or output gate as well. It was used in the calculation of new candidate value of cell state as well. And eventually it was used in the calculation of memory state at time t implicitly. So now we don't know what HT is at point t or at time t. So the hidden state is the element-wise multiplication of two vectors, which is the output gate and the tan hyperbolic value of the cell state. What this element-wise multiplication means is like this. If I have a vector a1, a2, and a3, and if I have another vector b1, b2, and b3, the element-wise multiplication is equivalent to getting a vector like this: a1, b1, a2, b2, and a3, b3. That's it. So in terms of numpy, whenever we have to create a dot product between two vectors, like if this is the vector a and this is the vector v, usually write a dot dot b like this in numpy we write. If we take two vectors and do a star b, then that's exactly what is the Hadamard product which we are seeing over here, the element wise multiplication which is happening. And the output vector is going to be v of st, because we already have a cell state. Cell state is actually going to be used for making the predictions. Hidden state is going to be used for updating the gates, and there is a bias term. This remains from RNN only. So this is exactly what we did in RNN, and this is exactly what we are doing in LSTM as well. And this will help us in completing the entire architecture. So just to summarize, these are the equations which we have. So based on the input value xt and the hidden state ht minus 1 of last state, in RNN ht minus 1 and st minus 1 were treated as the same thing, but over here both are treated differently. So the hidden state will be used in updating the gates as explained. So input gate is updated, the forget gate is updated, output gate is updated, and the possible candidate for cell state is also updated with the hidden state and the input vector, along with few biases and weights which we are going to tune when we are doing the back propagation. And this is how the updation is going to look like of the cell state. Now for the hidden state, the updation is just going to be the component wise multiplication of two vectors ot and tan hyperbolic st. Ot is like the output gate, and The tan hyperbolic st is the tan hyperbolic of the cell state at time t, and once that we have found out, then we can calculate y cap t, or the prediction at time t, as a function or an activation function of vst plus c. It could be anything. Activation function g could be tan hyperbolic, softmax, or even a ReLU, whatever is feasible, we can do that, and this will give you the final result. So this is how the entire architecture of LSTM looks like in mathematical terms. Just to understand things properly, I will take an example from Czech and explain it in a better way. So just take this example that we have an LSTM network with one hidden layer of 20 nodes used for predicting the next word in a text corpus. We don't have a bias over here, which will mean that all the bias terms will be zero. The corpus is of length 1000 words, and there are 100 unique words. And we have to assume a 10-dimensional word embedding module whose output is fed to the predictor LSTM network, and we have to find the trainable weights in LSTM network. So let's look into this question one by one. Like, first thing we know is like xt is a 10-dimensional word embedding. It is mentioned over here. Assume a 10-dimensional word embedding module, which will mean that xt will be having a shape of 10 cross 1. And ideally, when you are talking about word embedding, you will be getting something like this, like 0 0.5, 0 0.1, 7, 11, 19, something like this. This is the word embedding, which will go as an input. We will start with the input gate over here and slowly and gradually proceed with the other gates and see how it works. So this is the formula for the input gate we are considering. Note that since it was mentioned that biases are all zero, we put the BI as zero over here. Just focus on WI and UI only, which are going to be our parameters. Now let's try to see, while we need to train WI and UI, what is the dimensionality of WI and UI. So we start with xt. We just discovered that xt is of size 10 cross 1, because this is an input vector of embedding size 10. Then we proceed with ht minus 1. ht minus 1 can be found out easily from the assumption which is given in the question, that we have an LSTM network with just one hidden layer of how many nodes? 20 nodes over here, which will mean that ht, because there is only one layer, that will be 20 cross 1. So ht is going to be 20 cross 1. Now eventually we are going to get something like this it is going to be like 20 cross 1 only. Now in order to facilitate that, what is the value of wi, or the what is the dimension of wi, we need to choose 20 cross 20 so that the multiplication happens. The value of ui needs to be 20 cross 10 so that the multiplication happens, and on doing so we get ui of size 20 cross 10 as I showed over here, and wi of size 20 cross 20. Now we proceed further and see how exactly in other nodes things are getting changed. Now this is ot, which is the output gate. In output gate as well, we follow the same trend, like ht minus 1 and xt is going to be fixed for all the four possible gates which we have. Likewise in wi, w naught is of size 20 cross 20, u naught is of size 20 cross 10, and likewise wf uf is going to be of the same 20 cross 20 and 20 cross 10. And on doing so, from the gates which we are having and the possible candidate, these are the number of parameters which we are getting, like 20 cross 10 repeated 4 times, 20 cross 20 repeated 4 times, 2400. This is what we are getting. Now then we proceed further. If we see the equation which we have till now, so all these four gates are significant enough to get the cell state. The cell state has no parameters over here to means tune, I should say, because we have already determined, I think, around three gates, ft, it and gt. Then you will be easily able to find st. There is no parameter tuning involved over here as well. There is no parameter tuning involved in calculation of ht as well, because ot and st are already calculated. You just have to do the component wise multiplication of two vectors. The only requirement of a parameter will be at the last step. So we need to find out the dimension of vst. C is definitely not there, so only dimension of v needs to be determined. Now let's see what happens over here. So V is supposed to be a vector where there are 100 unique words which should be present. So amongst the 100 unique words, there is going to be one word which could be predicted. This is ideally a multi-class classification problem which we are dealing with, which will mean that there is going to be 100 probability values, and the value which has the maximum probability will be picked as the next word. Even though the corpus is of length 1,000 words, you don't have to be like very much strict on it. It might be like more than once a word is repeated. But over here, the main important criteria is the fact that there are 100 unique words. So we already know what is the output dimension of W is going to be. The output dimension of the, sorry, not W, V. Output dimension of V is going to be 100, because we need to make a prediction of 100 elements. Like 100 elements should be there in the prediction. And now ST is getting multiplied. Now ST is of shape 20 cross 1. So in order to make the multiplication possible, V should be of shape 100 cross 20. On doing so, we get 100 into 20 elements to tune. And on adding everything, like 2400 previously plus 100 into 20 elements now, so this is exactly the number of trainable parameters we need to consider for this LSTM network. So the problem started pretty simply with the fact that XT is an 10-dimensional word embedding, and then we consider like 4 gates and all the parameters which went into getting the 4 gates, and we were able to conclude that U and W are going to be of the same dimension throughout in the 4 components which we considered. There were 3 gates actually, and GT is the possible cell state over here. So U is of 20 cross 10 and it got repeated 4 times, and W was of 20 cross 20 and it repeated 4 times. We get the total parameter set from gates only as 2400. And now to consider that, we have to get the prediction vector V as well, which we were able to get it quite comprehensively on analyzing that ST is going to be a vector of 20 cross 1. We were able to find that V is going to be a vector of size 100 cross 20, and then we were able to find the total trainable parameters as 4400. So this is how we find the total trainable parameters in an LSTM. We are not discussing the backpropagation in both RNN and LSTM as of now. We are just trying to understand the architecture of both the algorithms. And from what we can see, if we place the LSTM algorithm as it is over here, and then we look into the vanilla RNN architecture over here, we see a lot of differences being made. First difference is in the form of cell state and hidden state, which we have made it quite clearly over here. And one of the state is used for updating the gates, which is the hidden state used for updating the gates, and the cell state used for eventual prediction. So this is how the LSTM works like. Now we will proceed further to another architecture which is called as gated recurrent units, or GRUs. In GRU, unlike LSTM, there are going to be only 2 gates. In LSTM, we had input, output, and forget gate. Over here, we have reset and update gate. So the reset gate determines how much of the past knowledge to forget, much like the forget gate in LSTM. And the update gate determines how much of past knowledge to be passed on to the future, much like how the combination of cell state and the output gate used to function. Now, the usual definition is pretty simple. But and first of all, if this is like how much of past knowledge, if this is the objective, then a percentage will be involved, and for that we use a sigmoid activation function over here. And the weights are exactly along the same lines as we had been doing previously from vanilla RNN till LSTM till now. And now the new candidate value for the cell state is calculated like this. This is the GT, which is the new candidate value of the cell state. So it is the tan hyperbolic of, there is going to be a parameter WC, RT and HT minus 1. RT we just calculated above. HT minus 1 is the hidden state at time t minus 1. And then this is exactly the parameter which we associate with the input state or the input value, and this is the bias. So overall, instead of having something like ht minus 1 over here or st minus 1 over here in this entire place, we just consider rt into ht minus 1. And just to see what rt is, it is the reset gate which determines how much of the past information to forget. Now we get the candidate value, and then we get the hidden state value, and this hidden state value is exactly same as the cell state value. We don't have a separate hidden and cell state doing the task for GRU. And the update gate takes care of it. Like, we know how much of the information should be passed on. We multiply with ut, and which is the update gate at time t, the formula for which is calculated over here. So if I see a possible candidate value, how much of it to be incorporated and how much of it to be not incorporated, or how much of the past information to be incorporated with the new candidate cell, that is being taken care of over here. Like, ht minus 1 is multiplied with some 1 minus ut. It will be like, if ut is 0.8, it will mean that 80% of the new candidate value needs to be incorporated, and 20% of the previous hidden state value having some information needs to be incorporated in order to update the hidden state. Now these cell state and hidden state both are same, st and ht are same, and eventually the output layer calculation is exactly the same as we had been doing across all the three networks. Like, it is going to be a vector v multiplied with st plus a bias c, and eventually we get the predicted values. The only difference being the fact that the thin line of demarcation between st and ht is completely removed over here, and the cell state and hidden state both are similar in GRU, which was not the case when we were talking about LSTM. So I think that's it from the explanation of GRU and LSTM from equation point of view. So in next video, we are going to talk about how the attention works when we have an encoder decoder architecture. And that's it from today's video. Thanks for your time.